Okay, so hello everybody. Welcome again to this awesome series of seminars by Quantum Spain, Talent Q. I'm very glad to have you here again. And this week, we have the pleasure to have with us Professor Diego Andrade Canosa. Diego is a colleague of mine. I'm very glad to have him as a close colleague. And he's a research professor at the University of La Coruña, where he made his PhD in 2008. He's a specialist in high performance computing. He belongs to the Department of Architecture of Computing Architecture of Computers. And today he has come to give us some highlights on benchmarking. In particular, he belongs to a big project called NEASQC, of which he will tell us about. So the title is Benchmarking Quantum Computers, the NEASQC Benchmark Suite TNBS case. So, Diego, thanks for being here, and the floor is fully yours.
Okay, thank you, Javier. Thank you for the invitation, and thank you also for your introduction. As Javier said, the topic of today is benchmarking of quantum computers, and I'm going to focus specifically in our contribution on this topic that was made in the framework of the NEASQC project, and this contribution is the NEASQC Benchmark Suite that we are going to call in our presentation TNBS. So first of all, let me introduce you the topic of benchmarking. Benchmarking is a general methodology which is widely applied in different fields, including also computer science. And in computer science, we are going to evaluate both the software and the hardware performance. And in general, if we focus on the architectural stack, and if we go from the hardware level to the software level, we are going to start with the hardware devices that we are using, and they can be a processor or accelerators such as GPUs. And then on top of this, we have the software stack, which is composed of the compilers, but also of the languages and the algorithms and the specific implementations that we provide from these algorithms. In classical computer science, benchmarking is a well-established discipline where we can identify several de facto standards. One of them is spec CPU that allows you to evaluate the performance of a processor, a central processing unit. At the level of the supercomputer facilities, we have, for instance, the top 500 list of the most powerful supercomputers in the world, which are listed based on its performance executing a specific benchmark, which is called LIMPAC. Also, we have the NAS parallel benchmarks, and sometimes we don't focus necessarily in performance, but for instance, we can focus on evaluating power efficiency. So the top 500 list has a power efficiency counterpart, that is the green 500 list, and also the spec CPU benchmark has a power efficiency counterpart, that is the spec power benchmark. We could list many other approaches, but it's just a small summary of some de facto standard. If we look into all these alternatives that we have in classical computing, we can detect or identify several common characteristics that I list here explicitly because I believe they are going to be very relevant also for the benchmarking of quantum computers. The first characteristic is that the benchmarks that we are going to execute are chosen because they are representative workloads of the things that you want to do with a classical computer. Sometimes these workloads are taken from the kernel level. For instance, in classical computing, linear algebra operations such as matrix multiplication are very popular benchmarks. Other times we have workloads that are defined at the application level. For instance, we can have something like a computational fluid dynamic simulation. And other times we have synthetic benchmarks, which doesn't belong to any specific application, but they are explicitly designed to stress certain characteristics of the hardware. Another characteristic that is important about all the benchmarking methodology that we have in classical computer science is reproducibility. Because when we want to compare, for instance, two processors, we should try to keep as constant as possible all the other components of the execution stack. So for doing this, every time we execute a benchmark, we have to keep record of all the information that is relevant about the execution stack. For instance, in a classical computing, the amount of RAM memory that you have, the technology of the dynamic RAM memory, or in the software part of the stack, the compiler that we are using, the flags of the compiler that we are using, etc. And then finally, all the benchmarks have to have several standardized metrics to measure the performance of the accuracy. In the case of the performance, sometimes we measure just pure speed, such as the wall time, the execution time from end to end, from the beginning to the end of the execution, including everything that is required to perform the execution. Also, we have the speed up with respect to a reference machine that is usually very slow. So the speed up is going to be most of the time greater than 1. And also we have productivity metrics such as MIPS or gigaflops, and also some variants that target power efficiency, such as gigaflops per watt. In the classical world, it's not so usual to target accuracy as scientific applications are usually doing or performing exact calculations. But in the case of machine learning, for instance, it's becoming very relevant to have accuracy metrics. So in machine learning models, we can have metrics such as the F1 score or perplexity. So moving already to the quantum world, the benchmarking of quantum computing is going to inherit some of the characteristics that we mentioned before. So first of all, we have to establish the quantum architecture stack, including both the software and the hardware layers. So at the topmost level, as you can see here, we have the applications or the algorithms, which are different from those that we have in the classical world. So we are going to have here quantum phase estimation, amplitude estimation, quantum optimization, quantum factoring, etc. And then we are going to have the programming languages or the software development kits that we are using for their implementation. Then going down to another level, we are going to translate this code using a compiler to an assembly language. And this is going to compose a given logical circuit. And this logical circuit has to be transpiled to the physical reality of the qubits and the interconnections that they have using the transpiler. So at the physical level, we can have a real platform with real qubits, real quantum gates, real fault tolerance techniques, etc. Or we can have a quantum simulator or an emulator. So the topic of benchmarking in quantum computing is a very active topic of research, where there are two main families of approaches. Some of them operate at the hardware level, and in here are especially relevant all the contributions from IBM, like all the work related to the quantum volume concept, and also more recent metrics such as error per layer gate or circuit layer operations per second. So the idea of this is that instead of having a real circuit belonging to a real application, what we are going to have is a synthetic circuit that is designed to stress certain characteristics of the hardware. And what we are going to measure here is not the accuracy of any real computation, but the fidelity of the qubits and the fidelity of the gates or the errors that we are making with the quantum platform. Our approach, however, is located at the other end, in the family that is called application-oriented. So this is our approach, TNBS, but in here we have other approaches that focus on the implementation of representative workloads of the type of applications that you usually want to do with quantum computers in real-world applications. So beyond ours, you can find in this category Munich Quantum Benchmark, Supermark, or Atos Q-score. And also, I would like to finish this slide talking about the national efforts, because benchmarking of quantum computers is becoming so important that even states are promoting their own national initiatives, like the DARPA initiative from the USA or the BAC project from Beatrix, France. So focusing already in our own approach, that, as I told you before, is application-oriented, I'm going to focus to talk about first about the framework in which this benchmarking was developed, which is the NEASQC project, NEASQC Applications of Quantum Computing, that has finished a few days ago. The intention of this project was to bring together academic experts and industrial partners in order to develop applications that can take advantage of NEASQC hardware in the future for solving problems of industrial interest. The specific objectives of this project was to develop 9 industrial use cases where practical quantum advantage could be proved using NEASQC machines of hardware. And also we develop open source libraries for these industrial use cases, and we build a user community dedicated to industrial NEASQC applications. Among our contributions, the one that we are presenting here is the benchmarking methodology that I'm going to tell you about. So this benchmarking methodology gave birth to a benchmarking suite that we call the NEASQC Benchmark Suite, TNBS, and was developed mainly by CESGA and UDC, although with very good contributions from Evident company as part of the NEASQC project. Also, other partners of the project contribute to the suite because they were specialists in different areas of application of quantum computing. So they allow us, or they help us to identify the kernels or the tasks that are common to one or several quantum computing fields of application. They help us also to identify a test case for those benchmarks. I'm going to tell you later what a test case is in our suite. And also they collaborated in the documentation that, as we are going to be about to see, is very critical for our methodology that is accurate and that allow us to be a base to implement every benchmark. So the TNBS suite gathers in one suite all the developed benchmarks in different use cases of the NEASQC project. And these are some key characteristics. One of them is that they are application-oriented. So this means that they are composed of several independent benchmarks that are extracted from real use cases of quantum computing. These benchmarks are defined at the procedural or the mathematical level. This is an extremely important characteristic because normally in benchmarking, what you see is that they provide you the reference implementation. But in our case, we decided to define the benchmarks at the task level, giving a mathematical or a procedural definition of what the benchmark has to do. And then Obviously, we provided a sample implementation, but any manufacturer can generate its own implementation of the benchmark following their own standards or their own guidelines that usually suit better their own platform. The benchmarking is trying to evaluate the performance of all the components of the stack at the same time. All the benchmarks can be configured for a wide range of number of qubits. So this is suitable for this era because we can define every benchmark, for instance, for 4 qubits, for instance, and also we can extend it, the benchmark case, to use, for instance, 1,000 qubits. Okay, so we have this freedom to configure the number of qubits that we want to use in a given problem. The outputs are classically verifiable, so this is also important because we can verify the outputs by classical means. So we are going to have metrics for the accuracy of the calculation, and the performance and accuracy metrics may be different for every benchmark. So overall, the philosophy of our benchmarking methodology, the question that we are trying to answer is that if a quantum platform that we want to evaluate is suitable or not for your problem or your application. Normally, when you buy a quantum computer and you are a company, you want to use the quantum computer for a specific type of application. So having several types of benchmark cases, maybe you are going to find one that suits your needs very well, and then bringing information about the performance of the quantum platform in that specific benchmark case is going to give you valuable information about if the quantum platform is suitable for you or not. Now, I'm going to introduce you some terminology about TNBS. The first one is the kernel. The kernel is the core quantum subroutine, which is defined at the highest possible level, mathematically or procedurally, and preferably it has to be something that is used in several applications. So for instance, in our case, a quantum phase estimation is going to be a kernel, okay? And obviously this can be implemented using different algorithmic procedures, but our proposal is not linked necessarily to any of these approaches. The second component is the benchmark test case. So associated to each kernel, we have a problem whose solution involves the execution of the kernel and whose output is verifiable through classical means. So this is going to be used to evaluate the performance of the kernel in a real context, in a real application, and it has to be equipped with a standardized procedure of execution. So the execution of the benchmark test case has to follow a certain number of very explicit steps in order to be reproducible and in order to be comparable to other executions or implementations from other implementers. And then we have the metrics that tries to evaluate the accuracy, in the case of the verification metric, answering the question of if the result is correct and is not, which is usual, to which extent is not correct. And also the performance metric that tries to answer the question of how fast we can solve the problem. Okay, so in this case, normally we are going to have the execution time, and normally this execution time is going to be decomposed in the classical part of the execution and the quantum part of the execution. Then once the benchmark test case is generated, we are going to generate an output. This output is going to be a large test file with a JSON format containing information that tries to contain all the metrics that we have gathered during the execution, including accuracy and performance metrics, but also many other components the start of the execution in order to make the execution reproducible. So we are going to gather information in this output about the quantum platform, the execution stack, like the compiler that we use, the version of the compiler, the transpiler, if we use any specific optimizations from the transpiler, etc. Okay, and all this information will be uploaded in the future in a month or so in our centralized TNBS repository to be officially compared to other executions of the same benchmarks. So the TNBS methodology has a document that are the TNBS guidelines. That is another deliverable of the project that contains the method of the template to generate new cases. And also it contains a complete documentation of the 4 cases that we have already proposed. The benchmarks that are proposed are extracted from the use cases of the NEASQC project. For every benchmark, besides the mathematical or the formal description, we have a sample implementation using EvidentMyQLM, and also we have a repository of the code where you can download the code and test it yourself. So now I would like to talk one by one about the 4 benchmark cases that we have identified in our benchmarking methodology, which are the probability loading, the amplitude estimation, the quantum phase estimation, and the parent Hamiltonian. And these benchmarks are called equally to the kernel in which they are inspired. Okay? So the first one is the probability loading. As this is the first one that I'm going to introduce, I'm going to explain to you the template that I'm going to use to introduce the different benchmarks. First, I'm going to tell you about the kernel. Then I'm going to tell you where this kernel is used, in which type of applications is used. Then later, I'm going to tell you about the benchmark test case that we are using for this kernel and the detailed execution procedure. And then I'm going to tell you several details about our example implementation of the benchmark and the algorithmic approaches for the implementation that we tested. And finally, I'm going to tell you about the verification metrics that we have used for each specific case. So let's start with the first one. The first one is the probability loading microbenchmark. The task of the kernel is to build a unitary operator U for loading a discrete probability distribution P into the amplitudes of a quantum state. This is the formal definition. So the idea is that if we have n qubits, we are going to have 2 to the n possible states, and each one of these basis states is going to have a given probability that we are going to use as an input. All this probability has to be normalized, so they have to add 1. And then the idea is that with a quantum circuit, we have to build a unitary operator that loads this probability distribution into the quantum circuit. This way, when we measure the execution of this the output of the execution of this unitary operator, we are going to get state 0 with probability P0, state 1 with probability 1, and so on. So the applications of this are many. This is a very common building block of quantum computer. This is used in HHL, also in principal components analysis, or in algorithms such as quantum amplitude estimation. There are many methods that can be used to implement this. Actually, in 2 of the deliverables of the project, they make a very thorough state-of-the-art review of many methods that can be used in order to implement the kernel of probability loading. The benchmark test case remember, is a real application where the kernel execution is required and whose output is classically verifiable. So in this case, we are going to use as a benchmark test case the loading of a non-Gaussian probability distribution that we know in advance. So this is the form of the formula of the probability distribution, and in the left part of the execution procedure, we are following several steps like fixing the number of qubits, and then from there we are going to create an array of probabilities according to this Gaussian distribution. The idea is that this part of the execution procedure of the benchmark test case is the classical preprocessing. So at the end of this classical preprocessing, what we have is an array of probabilities associated to each possible quantum basis state. So these are the probabilities that we have to encode using the unitary operator. So we create this operator using one of the methods available in the literature. And then once we have the operator, we execute the circuit a number of times and measure the output. So at the output, we are going to get a given basis states. And the idea is that we are going to measure the probability of having each possible state. So the number of shots of the circuit is designed or calculated to produce the result with a given confidence interval, and the output of this repeated execution of the benchmark test case is an array of probabilities Q that are the measured probabilities in the output of the circuit. Ideally, if the method is perfect, the array of probabilities Q will be equal to the array of probabilities P that we use as an input. Okay, so our idea is that the better the quantum platform works, the more is going to be similar the Q array of measured probabilities to the P array of initial input probabilities. So in order to implement the unitary operator, there are several methods. Some of them are classical, like the 2002 proposal from Brassard, and they are based on rotations controlled by state. The original approach follow a direct brute force approach, but there is another approach based on quantum multiplexers from 2006 from Schande that makes a less deep circuit. And actually, if you look at these two sample circuits, you can see that for building the operator, if you use the brute force, you are going to have a circuit like this. But if you use the method of quantum multiplexers, you are going to have a shorter circuit. Okay, so this approach is supposed to be better, but maybe in some quantum platform, this implementation is going to work better. So it's up to you as an implementer to use the one that you prefer. Actually, in our GitHub repository, we tested both approaches, and both of them are available in our example implementation. Regarding the metrics, we don't mention in our cases the verification metrics because the execution of the performance metrics, because normally in that case we are going to use the execution time, decomposing separately the classical time and the quantum time. What we are going to use differently in different benchmark cases are the verification metrics. In the verification metrics, in this case, we are going to compare two probability distribution. And in order to do this, we have many tools in statistics. So we pick two of them. One of them is Kolmogorov-Smirnov, and the other one is Kullback-Leibler divergent. In both cases, the closer to zero, the better. So if the two probabilities were the same, then we will have that this metric will be 0 and this metric will be 0. But the higher the value is, the more are different the probabilities encoded in P and the probabilities measured in Q. So moving forward to the next benchmark case, this is the amplitude estimation micro benchmark. In this case, the idea is that we are going to build an unitary operator A of the amplitude estimation kernel, and we want to find the amplitude of a fixed substate size 0 of interest that we are going to call the good state. So we want to estimate, given the state psi, we apply the operator A on the qubits initialized to 0, and we are supposed to obtain size 0 with a given probability. So this is going to be the square of the amplitude. And then with the complementary probability, we are going to get a bad state, psi 1. So the applications of this are many. This is a kernel or a building block that is commonly used in finance, chemistry, and numeric integration. And there are many methods, many algorithmic approaches to implement this. Normally, most of them are based on the application of the Grover operator on the unitary operator A and then post-processing the result. But in some cases, we are going to use the quantum phase estimation for getting the value of A. And in other cases, we are going to use an iterative algorithm. See that this is a perfect example of how important is not linking our benchmark definition to any algorithmic implementation. In this case, probably in this hardware, the solution that is based in the application of the quantum phase estimation is not going to work at all. So probably in this era platforms, you are going to prefer an interactive algorithm. Okay, but maybe in a few years we are going to have better platforms, and in that case, you are going to prefer to use the quantum phase estimation because it's going to be physically possible to implement. Okay, so this is a more formal definition of the kernel. We are supposed to have a unitary operator that creates a state size 0 with a given probability that can be easily quantified. And in the complementary situation, is going to produce not that state, but another state. We can use a Grover operator that doing reflections around the 0 axis and the size 0 axis is going to amplify the probability of the good state. So also we can apply this Grover operator a configurable number of times, k, to further amplify the amplitude. So in order to get A, the amplitude of this good state, we can use the quantum phase estimation using in the framework of quantum phase estimation the Grover operator, and we can use an interactive algorithm, which is usually based on the application of the unitary operator, then the Grover amplification operator a configurable number of times, k, and then doing some measurements. These measurements are going to give me a lower and upper bound for the value of the amplitude. So the algorithm is iterative because if the lower and the upper bound are close enough, I'm going to finish the execution, but if they are not close enough, then I'm going to adjust the value of k, and I'm going to start a new iteration of the execution of the iterative algorithm. So in this case, in the amplitude estimation, the benchmark test case that we have used is the integration of a well-known function, which is the sine function. Obviously, there is no point in doing this, but the importance of the integration of the sine function is that it's very easily classically verifiable. Actually, if we integrate the sine function between A and B, this is trivially the cosine of A minus the cosine of B. And in the benchmark test case, we are going to propose to the platform two different intervals of integration. One that is going to produce a positive result, and another one that is more challenging and that is going to produce a negative result. So the question is, for this specific benchmark test case, how we are supposed to build the unitary operator A, and how, once we have created this operator, how can we use amplitude estimation in order to estimate the value of this function, of this integral expression. So in order to do this, we have designed this execution procedure for the benchmark test case. The first steps, as it happened in the other case, are going to be just for discretizing the domain and creating different values for different points of the integral. And at the end of this classical preprocessing, I'm going to approximate the value of the integral using a Riemann sum. So in here is where the quantum part starts. First, we have to create an operator that corresponds to the encoding of the f function, being the f function, the integral of the sine function in a given interval. And once we have built this operator, we have proved that this operator, the eigenvalues of these operators, are going to produce the appropriate value that can be used to calculate that integral. Okay, so at the end of this process, and using the algorithm of amplitude estimation, we can extract a value that can be classically transformed in a very direct form to generate the value that we want to calculate. That is the integral of the sine function in a given interval. So at the end of the process, we want to compare the value that we have produced with the quantum platform with the approximation of the Riemann sum. And the closer the two values, the better. So again, in this case, we have many methods in the literature to do so. The three first methods that we list here only consider the positive interval, and only the last method is only to achieve the right result also in the negative interval. Okay, so you can see that again, for the implementation of the kernel, and conversely, for the implementation of the benchmark test case, we are going to have many algorithmic approaches. So in order to verify the output, we are going to use the absolute error between the ground truth, which is the approximation with the Riemann sum, and the output of the quantum circuit. Okay, and this absolute error is going to be a good measurement of the accuracy of the circuit. Okay, so I'm going to skip this one, the quantum phase estimation, because I don't have time for everything, and I'm going to move forward to this case that I believe is more interesting, and is the parent Hamiltonian. The parent Hamiltonian, the kernel in this case, is that given an ansatz with an state psi de theta, we can calculate, or we can elaborate something called a parent Hamiltonian, such that its ground state is going to have energy equal to 0. Okay, so you can see here the formulation. We have this state prepared by the ansatz, and with this state, there is a parent Hamiltonian that we can produce algorithmically and whose expectation value for the energy is equal to 0. This has many applications, obviously, in variational quantum algorithms. For instance, in BQE, in our benchmark test case, we are going to use an ansatz with a very specific type of layers. So this type of layers is very common shape for an ansat, where we have different rotations in different axes with fixed angles, and then a ladder of control gates. So in the benchmark test case, first we have to produce the parent Hamiltonian, and in order to produce the parent Hamiltonian, we have to fix the number of qubits and the number of layers of the ansat, repeating this several times. Then we set the angles that we have to use for that specific ansat. That depends on the number of layers. They are calculated with an expression that depends on the number of layers. And then we solve the state of the ansat. We apply with these angles, we execute the ansat, and we get the output. And with this output, we are going to compute algorithmically with a method that is well known in physics, the corresponding parent Hamiltonian. And then this parent Hamiltonian, as is usual in this kind of application, is going to be decomposed using Pauli matrices. So having this, and in the context of the algorithm, we are going to use this Pauli string decomposition from the parent Hamiltonian to measure the output of the ansat in different bases. And this is going to give me one by one the different expectation of the value in the different Pauli string decomposition where we want to measure the output. And at the end, once we have finished processing all these measurements, I'm going to get an expectation value for the energy. And as the parent Hamiltonian was built on purpose to produce energy equal to 0, the output of this has to be 0. And if it is not 0, this is not right, okay? So in that case, what we are providing here is that we are providing the Pauli decomposition for ansatz from 3 to 30 qubits and from 1 to 4 layers for each qubit, but also we are providing an implementation for calculating the parent Hamiltonian and its Pauli decomposition using the MyQLM library, and also we have a faster implementation of this procedure using matrix product states. Also, I would like to talk that Evident produced an alternative implementation of all the benchmarks using as a base only the benchmark specification documentation at the mathematical and the procedural level. And with that implementation, they produce emulations of the benchmarks using noisy platforms. And these noisy platforms use different types of noise, okay? And these are the type of noises that they use. So I'm going to show you just the results of two of the benchmarks. The first one is the probability loading. In the probability loading, I'm reporting just the KS metric, and in the KS metric, this will be the ideal case. Okay, so remember that here, the lower the better. And then we have a noisy emulation inspiring an IBM platform, and this one is a noise emulation inspiring a quantum platform. So in these cases, in all these cases, the lower the better, because the ideal value for the error or for the divergence in this case is 0. The same test for the parent Hamiltonian, although in this case the emulation only achieved a circuit of 4 qubits because the circuit is quite complex, and obviously this is very hard to provide a noisy emulation. So they have the results for the ideal scenario, for the IBM noise scenario, and for the quantum scenario. And remember that in this case, the closer to 0, the better. So those platforms where you see that you are very close around 0, very tight around 0, are those that are performing better, okay? So finally, I don't have much time left, and I would like to leave some time for the question, I'm going to put you just the link of the repository of the code and some of the key documents of the benchmarking methodology. And actually, at the end of the presentation, if you want, you have the QR codes in order to be able to check our TNBS documentation and also our code repository. And thank you very much. I would like to have more time, but obviously I want to spend some time answering your question. Thank you.
Thanks a lot, Diego. Thanks very much. Very clear and very didactic, very pedagogic. So, the background is there for anybody to make questions. You just raise your hand, and Javier will unmute you so that you can ask any question. I'm sure there will be questions in the audience. So don't be shy. I mean, we have plenty of time. Anything that has been not fully clarified can be clarified now. Yeah. Okay, so I would like to know. I mean, I was curious about this parent Hamiltonian. How was exactly the benchmark in the end? So I missed that. So could you go back and
in BQE, normally in the step of execution of BQE, variational quantum eigensolver, you have like a very clear pattern where you have a parameterized answer that these are the angles that you have to adjust in order in the interactive process. And then the Hamiltonian that is doing the right measurements in order to get the expectation value. So for us, the kernel was the whole package of the step of execution of a variational algorithm such as BQE. So this involves the answer and the execution of the measurements in the Hamiltonian.
I see. So I didn't see quite. So there's some questions here in the chat. Jaime Gomez Garcia, can you put again the benchmark result on screen? Yeah.
This one or the parent Hamiltonian?
Well, I'm not sure. This is Jaime Rafael Gomez Garcia. I was just mentioning in the chat. Can you put again the benchmark result on the screen? Yeah, but there. So
he says next one, please. He says.
Parent Hamiltonian. Okay.
Yeah. Is there any question, Jaime, there?
Yes, Venkatesh has a question. Venkatesh, your micro is open.
Thank you, and thank you very much, Diego, for the presentation. So I had one question, your thoughts on it. In the context of some of the work that we are doing in resource estimation for evaluating quantum Hamiltonians or circuits on systems, we come across very similar questions like execution time, accuracy, depending on circuit characteristics, hardware characteristics, software characteristics. So I was wondering that there might be relevance in downstream use of this benchmarking suite and its outputs for the likes of resource estimation, where it can be design time decisions on how you compose these quantum circuits in terms of alternate gate choices, topology and things like those, and also runtime characterization before execution or resources are allocated for execution. Do you have any comments or thoughts on that? Because this benchmarking outputs could be used for some downstream applications which are not necessarily just for evaluation of the hardware systems.
So your point is that if a specific design of an answer works well with the parent Hamiltonian, should be a better or a more promising answer? Is that what you mean, for instance?
Yes, for example, yes, yeah.
Or that if you know how long is going to take the execution of a given package composed of a specific answer design,
answer design, gate set design, etc. Yes.
Yes, then you can estimate how good is for the balance between specifics of the answer and execution time a given possible proposal. I mean that when you have a very complex answer that is very expressive, probably this is going to adjust better to the problem that you want to solve, but maybe at the runtime is going to be so big or so large that, or even the optimization process is going to be so long, or it's going to take so long that it's not going to be good for the overall picture of what you want to do.
Yes, something like that. Okay. Okay. Thank you.
Okay. Okay. Thank you.
Okay. Yusuf. Yusuf, your microphone is open if you want to ask. Maybe it doesn't work, or you can write if you want. Well, let's go with
It
David.
was me. Oh, David. Okay.
Hello? Can you
Hello?
hear me?
Yeah.
Okay.
Yes.
Yeah, I would like to ask which of these benchmarks scale polynomially with the number of qubits, because most of them need some classical part, and this classical part maybe it's not good. It's not enough for the number of qubits not scaled correctly.
Yes, this is an open discussion in the people that we are doing the benchmark. That maybe for the current state of the quantum platforms, the amount of classical preprocessing that they are going to require is not too much, but maybe in the future when we have, I don't know, 1 million qubits or maybe 10,000 qubits, this is going to be unaffordable. A perfect example is the parent Hamiltonian. In the parent Hamiltonian, we produce the corresponding parent Hamiltonians to a given size of the answer, but obviously at that point, the computational requirements to produce the parent Hamiltonians are increasing. So this is going to be a problem in the future when we have a significant number of qubits. But in general, I believe, or we believe, that the classical pre-processing and the classical post-processing is going to be a big problem for quantum computing in general, not just for this benchmarking methodology. Because, for instance, in the case of the amplitude estimation, as the integral of the sign can be calculated subtracting the cosines, that should be easily calculated. There is no need to approximate it through a Riemann sum, okay? So maybe this is going to be easier. But in other cases, like the parent Hamiltonian, the classical preprocessing may be a problem in the future when we have a significant number of qubits.
Okay. What about the relation between this number of qubits and the deep of the circuit? Because, for example, when you are doing like function loading, the deep of the circuit will depend of the number of qubits, or that's not a problem for the moment.
Well, so far the circuits that we have produced are quite balanced. They have a good balance between width and depth. But obviously, for instance, in the case of the parent Hamiltonian, again, you can stress the depth of the circuit as much as you can. For instance, here, you can put 2 layers like here, but you can put 100 layers. But maybe this is something that you want to stress explicitly to a certain extent. So from that point of view, this approach, for instance, of the parent Hamiltonian is going to give you a big configurability with respect to be able to module the depth of this part of the circuit, for instance.
Okay. But in just in the case of function loading,
probability loading.
Probability loading, yes.
Yes.
In that case, the depth of the circuits depends also of the width of the circuit too.
Yes. In this example, you are not going to have you cannot control the balance between the width and the depth. And obviously, in this case, you are conditioned by the type of techniques that you use. Actually, we mentioned in the presentation that brute force method usually create deeper circuits than quantum multiplexers, okay? But obviously, even with quantum multiplexers, for some widths, the depth is going to become a problem.
Okay, thanks.
Okay, you're welcome.
Luke?
Hi, thanks. It was a really nice talk. So I saw that you applied these benchmarks to IBM and Quantinuum. How easy is it to apply this to other systems or other platforms that are available?
Well, we didn't apply the benchmarks to the real platforms, but to emulations of the noise models of the real platforms. So,
okay.
Yes, they were not the real platforms.
Right.
Okay. So because we didn't have access yet to these platforms, and we will be willing to do it in the future if they allow us to do it. But obviously, if you try to do something like a quantum phase estimation on real hardware, probably you are going to require additional techniques such as quantum tomography or things like that in order to get meaningful results or good results. The thing is that as we define the benchmark at the procedural or the mathematical level, if the implementer needs to use additional techniques for getting the right result, it's up to them to do it. Obviously, in our MyQLN implementation, in our example implementation, we were doing only emulation, so we didn't require any additional techniques in order to get the results right. Because I believe this is what you are asking about.
Yeah,
right?
That answers it. Thank you.
Yes.
So can I also ask about, so for the parent Hamiltonian problem, so I'm more familiar with VQE when you have a Hamiltonian, you try and you have a circuit which describes a state and you're trying to minimize the energy. But
Yes.
here it seems like you're trying to do the inverse, right? Given a state, how can I find some Hamiltonian which generates this as a ground state, let's say. So these A of I's, so you run your circuit, you take your measurement in respect to whatever basis you like, and then you have to take the sum of this with these A of I's.
Yes.
And so is the problem trying to choose these A of I's such that it gives you the Hamiltonian, or?
No, the technique of the parent Hamiltonian, that is a well-known technique in physics, is supposed to generate the parent Hamiltonian whose decomposition in Pauli strings is going to produce the energy zero. So I don't know if this answers your question.
Yeah, thanks. I think I get the general idea.
Yes, but actually, if you visit our repository, we have an implementation that, given an answer, is able to generate the corresponding parent Hamiltonian and its decomposition in Pauli strings.
Great, thanks. Yeah, I'll take a look. Thank you.
Okay, you're welcome.
And then there is a final question on the chat. Yusuf, that he couldn't speak before. He wrote on the chat. I don't know if you can see, Diego.
Sorry, because I have the slide.
Yeah, I can ask if you want. He says,
let me check.
About the parent Hamiltonian, how can you build it?
Well, I didn't implement that part, but there are a lot of implementations available over there. Most of them are narrow to or constrained to the physics world, but in our repository we have the implementation for that. And if he is interested about how we do it technically, I can keep him in touch with the appropriate person to explain it to him. But it took a long time to do.
Okay.
Yes, it's not a technique which is easy to master.
Okay, so I think we're almost done. And I want to thank you all for being here. I want to thank Diego again. And I want to reconvene you for the next talk in 2 weeks. So stay tuned and keep well, everybody. So thanks a lot and goodbye.
Thank you.
Thanks, Diego.
Thank you. Bye. Ciao.